Physics of the Impossible, a scientific exploration into the world of phasers, force fields, teleportation, and time travel, by Michio Kaku. Have you ever gazed up at the stars and wondered if we're truly alone in this vast universe? Have you ever wished you could slip into invisibility just for a single day? Or imagine traveling back through time to witness history firsthand, or perhaps even correct a regret that's haunted you. What if you could pass through solid walls like a ghost? Or build a starship capable of carrying you to distant galaxies faster than light itself? For most of us, these are the wild daydreams of science fiction. They're the fantasies we watch unfold in darkened movie theaters, the impossible tales we devour in books late into the night. They feel like pure magic, nothing more. But here's the thing. For one of the world's most brilliant physicists, these weren't just idle fantasies. They were the spark that ignited a lifelong quest to understand the very boundaries of what science can achieve. That man is Michio Kaku. Today, he stands as a world-renowned theoretical physicist, one of the pioneers behind string theory, a groundbreaking framework that might one day explain everything. But his remarkable journey didn't begin in some prestigious university lecture hall. It began as a young boy, sitting cross-legged in front of a flickering black-and-white television, completely mesmerized by old episodes of Flash Gordon. Every Saturday morning, young Michio was glued to that screen, watching rocket ships blast off, invisibility shields shimmer into existence, and ray guns fire brilliant beams of destruction. But he didn't just see a hero saving the day. He saw something deeper, a world powered entirely by science. He realized the real hero wasn't just Flash Gordon swooping in at the last moment. It was the scientist, Dr. Zarkov. Without science, there would be no rocket ship, no grand adventure, no saving Earth from certain doom. Without science, there simply is no science fiction. This love affair with the impossible only intensified as he grew older. When Albert Einstein died in 1955, young Michio saw a haunting photograph in the newspaper. It showed Einstein's desk at Princeton, and on it lay an unfinished manuscript, the work of the greatest scientific mind of the age, left incomplete at the moment of his death. Michio learned it was Einstein's final pursuit, a unified field theory, a single elegant equation that could explain every force in the universe. An impossible dream that even Einstein couldn't complete. That image, that unfinished equation, lit a fire in his soul. Right then, he decided he would follow in Einstein's footsteps, no matter how impossible the journey seemed. While most kids his age were building model airplanes from kits, Michio Kaku had bigger plans. In high school, for his science fair project, he went to a local steel company and gathered 400 pounds of scrap transformer steel. Then, over his Christmas vacation, working in his mother's garage, he wound 22 miles of copper wire by hand. His goal? To build his own particle accelerator, an atom smasher, right there in suburban California. This wasn't some toy science experiment. He built a fully functional 2.3 million electron-volt Betatron, a device so powerful it consumed every bit of electricity his house could provide, and generated a magnetic field 20,000 times stronger than Earth's own. He wanted to create a beam of energy powerful enough to produce antimatter, at 16 years old. That audacious project won him a scholarship to Harvard and set him firmly on the path to becoming the physicist he is today. In his incredible book, Physics of the Impossible, Dr. Kaku takes us along on that same thrilling journey. He revisits the dreams and fantasies of his childhood, those force fields and teleportation devices and time machines, but this time he examines them through the sharp, unforgiving lens of modern physics. His promise to us is both simple and profound. By the end of this journey, you will no longer see the world divided into neat categories of possible and impossible. Instead, you'll see it through the eyes of a physicist, and you'll understand that the things we casually dismiss as impossible today are often just waiting patiently for the right science, the right technology, and the right minds to bring them into reality. This isn't just a book celebrating science fiction. It's actually a roadmap to our future. So let's begin our journey into this fascinating world of the impossible. The first thing you need to understand is that not all impossible ideas are created equal. Michio Kaku gives us a brilliant framework for thinking about them. He divides the impossible into 3 distinct categories, and this framework will be our guide throughout this journey. First, there are what he calls Class 1 impossibilities. These are technologies that are impossible today, right now, but they don't actually violate any of the known laws of physics. They might become possible within a century, maybe a few centuries at most. Think of things like teleportation, certain forms of telepathy using technology, and perhaps even antimatter-powered starships. Next up are the Class 2 impossibilities. These technologies sit right at the very edge of our current understanding of the universe. If they're possible at all, it might take thousands, perhaps even millions of years for a civilization to develop them. This is where we encounter things like time travel, travel through hyperspace, and traversable wormholes connecting distant parts of the universe. And finally, there are Class 3 impossibilities. These are technologies that, as far as we currently understand, directly violate the known laws of physics. Things like perpetual motion machines that somehow create energy from nothing, defying the fundamental rules that govern reality itself. Throughout our journey today, we'll use this framework as our compass. It helps us understand that when a scientist declares something is impossible, they often don't mean it's impossible for all time. They mean it's just impossible for a civilization as young and technologically primitive as ours currently is. So where do we start? We need to start with the foundation of everything, the very forces that hold the entire universe together. In all of physics, across everything we've discovered, we've identified just 4 fundamental forces of nature. That's it. Just 4. Everything you see around you, everything you touch, every process from the smallest atom to the largest galaxy is governed by these 4 forces alone. The first is gravity. It's the silent, invisible force that keeps your feet planted firmly on the ground and holds entire galaxies together across millions of light years. But here's something surprising. As forces go, gravity is incredibly, almost ridiculously weak. Think about this for a moment. It takes the entire mass of planet Earth, all 6 trillion kilograms of rock and iron, to pull a single feather down to the ground. But you, with just one finger, can counteract that entire planet's gravitational pull simply by lifting that feather. That's how weak gravity truly is. The second force is electromagnetism. This is the powerful force that literally lights up our cities and powers our modern world. From radio waves and television signals to the internet flowing through fiber optic cables and the phone in your pocket, it's all electromagnetism. It can both attract and repel, which makes it incredibly useful. But it can also be easily blocked or neutralized. A simple piece of plastic or wood, for example, can pass straight through even the most powerful magnetic field without any effect. The last 2 forces are the strong and weak nuclear forces. The weak nuclear force governs radioactive decay. It's actually what keeps the center of our planet hot enough to maintain the magnetic field that protects us from solar radiation. The strong nuclear force is what binds the nucleus of every atom together, overcoming the electromagnetic repulsion between positively charged protons. It's the power source that makes the sun shine and every star in the night sky burn. But both these forces have a critical limitation. They're incredibly short range. They only operate over distances smaller than an atomic nucleus, which makes them almost impossible for us to directly manipulate on any useful scale. These 4 fundamental forces are the building blocks of all reality. Any technology we dream up, no matter how impossible it seems, must ultimately work within the rules set by these forces, or somehow find a clever loophole around them. And that brings us to our first class, 1 impossibility: force fields. In Star Trek, whenever the Enterprise faces danger, Captain Kirk's first command is always the same: "Shields up!" Instantly, an invisible barrier springs into existence around the ship, effortlessly deflecting laser blasts and enemy missiles. It seems so simple, so elegant. So why don't we have this technology yet? Well, when you examine the four fundamental forces, none of them seem to naturally fit what we need. Gravity only attracts, never repels. Electromagnetism can be easily blocked by simple materials. And the nuclear forces are far too short range to create any kind of protective barrier around a ship or a person. A true science fiction force field, as we usually imagine it, just doesn't seem possible with our current understanding. But, and this is important, that doesn't mean we can't create something that acts very much like a force field. Dr. Kaku points out a fascinating loophole: plasma, the fourth state of matter. You're familiar with solids, liquids, and gases, but plasma, which is essentially a gas heated to such extreme temperatures that electrons are stripped from atoms, creating a soup of electrically charged particles, is actually the most common form of visible matter in the entire universe. It's what stars are made of, and because plasma consists of charged particles, you can shape it, contain it, and control it using magnetic fields. Back in 1995, a clever physicist named Adi Hershkovich invented something remarkable called a plasma window. By heating gas to thousands of degrees, he created a flat, glowing sheet of plasma, suspended and contained by carefully tuned magnetic fields. This plasma window could actually separate a vacuum chamber from normal air, acting like an invisible barrier. When you use argon gas, it even glows with an eerie blue light, looking remarkably like the force fields we've seen in Star Trek for decades. Now, a single plasma window by itself couldn't stop something like a cannonball or a missile, but what if you got creative and built a multi-layered defensive shield? Imagine this layered defense system. The outermost layer would be a supercharged plasma window, heated to temperatures so extreme it would instantly vaporize most incoming projectiles before they could penetrate even a few inches. Behind that first layer, you'd have a second defensive screen, a dense curtain made of thousands of crisscrossing high-energy laser beams. These intersecting beams would create a three-dimensional lattice of pure energy that would heat up and vaporize anything that somehow managed to survive the first plasma layer. And for your third layer of defense, behind the laser curtain, you could position a screen woven from carbon nanotubes. These are microscopic tubes of pure carbon, just one atom thick in their walls, yet they're many times stronger than steel. If you could weave millions of them into an invisible mesh, you'd have a barrier that's practically invisible to the naked eye, yet stronger than almost any material we know how to manufacture. So combining a plasma window, a laser curtain, and a carbon nanotube screen, you could actually create an invisible defensive wall that would be nearly impenetrable to physical projectiles. It wouldn't be a true force field in the science fiction sense, but it would be remarkably close to the next best thing. There's still one significant problem with this design. This shield would be completely transparent to enemy laser weapons. To defend against directed energy weapons, you'd need one more technological component: advanced photochromatic materials. This is based on the same principle used in those sunglasses that automatically darken when you step outside into bright sunlight. The molecules in the glass exist in two different states, one transparent and one opaque. When exposed to ultraviolet light, they instantly switch states. If we could use advanced nanotechnology to engineer material that could instantly become opaque the moment it's struck by a powerful laser beam, then our multi-layered shield would finally be complete. It could defend against bullets, missiles, and directed energy weapons. Developing this kind of sophisticated shield system is probably still decades away, maybe even a full century. But here's the crucial point. It doesn't violate any fundamental laws of physics. All the components are theoretically possible. That makes it a clear Class 1 impossibility. Let's move on to another fan favorite from science fiction: invisibility. From Harry Potter's magical cloak to the cloaking device that makes Klingon warships vanish in Star Trek, the ancient dream of becoming invisible has captured human imagination for thousands of years. For centuries, physicists confidently declared it was completely impossible, because it seemed to violate the fundamental laws of how light behaves. But recently that confident dismissal has been turned completely on its head, thanks to a revolutionary discovery: metamaterials. To understand what makes metamaterials so special, we first need to understand a basic principle of how light works. When you stick a straw in a glass of water, it looks bent or broken at the surface. This happens because light slows down and changes direction when it passes from air into water. This bending phenomenon is called refraction, and it's completely normal. Metamaterials are artificially engineered substances implanted with carefully designed tiny structures inside them, things like microscopic circuits or precisely shaped metal components, that force light to bend in ways that simply never occur in natural materials found anywhere in nature. Imagine watching a river flowing smoothly around a large boulder. Downstream from the boulder, the water flows back together seamlessly, almost as if the boulder wasn't even there. A carefully designed metamaterial could do exactly the same thing, but with light waves instead of water. It could bend rays of light completely around an object, guiding them smoothly past it, making it appear as if the object has completely vanished from existence. There would be no reflection, no shadow, nothing. The object would be genuinely invisible. In 2006, scientists at Duke University and Imperial College in London actually built a working prototype. They created a metamaterial that successfully made an object completely invisible to microwave radiation. You could shine microwaves at an object, and they would bend around it, leaving no trace. This was genuinely historic, a true breakthrough. Something that physicists had declared impossible for generations had actually been achieved in a laboratory. But there's a significant catch that we need to understand. For a metamaterial to work its magic, the internal structures embedded inside it have to be physically smaller than the wavelength of whatever radiation you're trying to bend around an object. Microwaves have a wavelength of a few centimeters, which is relatively large, so the structures in that first metamaterial were fairly large and easy to manufacture. But the wavelength of visible light is incredibly, almost impossibly small. It's measured in nanometers, which are billionths of a meter. To create an invisibility cloak that works for visible light, you'd need to engineer a material with internal structures smaller than the light waves themselves. This requires sophisticated nanotechnology, the ability to precisely build and arrange structures at nearly the atomic level. The race is definitely on. Scientists around the world are adapting techniques borrowed from the computer chip industry, like photolithography, which uses light to literally etch microscopic structures onto materials. In 2007, a research group in Germany announced they'd created the first metamaterial that actually worked for red light, one specific color of the visible spectrum. They had achieved something called a negative index of refraction, which every physics and optics textbook for the past century had confidently stated was theoretically impossible. So what does all this mean for creating a real, practical invisibility cloak? Well, it's probably not going to be a soft, flowing fabric like Harry Potter's magical cloak, at least not at first. The initial versions would more likely be rigid cylinders, or boxes made from these carefully engineered metamaterials. You could hide inside it and become invisible to anyone looking at you. And there's another amusing problem nobody really talks about in science fiction. If you're standing inside a cloak that bends all light completely around you, making you perfectly invisible, then no light can reach your eyes either, which means you'd be completely blind while invisible. You couldn't see anything outside the cloak. One possible engineering solution might be to install tiny beam splitters positioned near where your eyes would be. Devices that divert just a tiny, almost undetectable amount of light into your eyes so you can see out. The progress in this field is happening incredibly fast, far faster than most people realize. Within just a few decades, we might actually have working invisibility shields, at least for certain specific colors of light. It's a perfect example of a Class 1 impossibility. Now let's turn our attention to the ultimate science fiction weapon, phasers and Death Stars. In Star Wars, the Death Star, that massive moon-sized battle station, fires a single, colossal beam of concentrated energy and completely vaporizes the entire planet Alderaan in seconds. A billion souls, an entire civilization, silenced in a single terrifying instant. Could such a devastating weapon ever actually be real? It might be hard to believe, but here's the truth. There is no fundamental physical limit to the sheer amount of energy you can concentrate into a beam of light. The laws of physics, as we currently understand them, do not actually forbid something like a Death Star from existing. In fact, nature has already created something far, far more powerful than anything shown in Star Wars gamma-ray bursters. These are titanic explosions occurring in deep space, second in power only to the Big Bang itself. Scientists believe they're caused by massive, dying stars collapsing catastrophically into black holes. As the star collapses in its final death throes, it shoots out two incredibly powerful jets of deadly radiation from its north and south poles. If a planet with life were unlucky enough to be caught in the direct path of one of these cosmic jets, it would be instantly sterilized, its protective atmosphere stripped completely away, its surface scorched clean of all life. A gamma-ray burster wouldn't just destroy life on a planet, it would essentially erase it from existence. So the energy required is definitely possible. Nature proves that every day. The real challenge is harnessing and controlling it. The weapons we see throughout science fiction, phasers, ray guns, lightsabers, they're all fundamentally based on lasers, which stands for light amplification by stimulated emission of radiation. A laser works by pumping energy into a special material, like a crystal or a gas, until its atoms are all in an excited, energetic state. Then, a single photon of light can trigger a spectacular chain reaction, creating an avalanche of photons, all vibrating in perfect unison. This creates a coherent, precisely focused beam of light that doesn't spread out like normal light does. Today, we actually have incredibly powerful lasers. Chemical lasers developed by the military can produce millions of watts of raw power, enough to shoot down incoming missiles in mid-flight or disable enemy satellites. Lasers are also used in cutting-edge fusion research. At the National Ignition Facility in California, 192 separate powerful laser beams are focused simultaneously onto a tiny pellet of hydrogen fuel smaller than a peppercorn, creating temperatures and pressures found only in the core of a star or in a detonating hydrogen bomb. So if we can build lasers this powerful, why don't we have handheld ray guns like in Star Trek? The problem isn't actually the laser technology itself, it's the power source. You would need a portable battery pack that could instantly deliver the energy equivalent of a massive power station, yet somehow be small and light enough to fit comfortably in the palm of your hand. Right now, the only genuinely portable device that can deliver that kind of energy density is a miniature atomic bomb, which is obviously not very practical or safe as a sidearm for your average soldier. And what about a lightsaber, like the Jedi use in Star Wars? A glowing blade of pure energy that can slice through solid steel doors like butter. The problem is, you can't really solidify light into a blade. A beam of light doesn't just magically stop in midair 3 feet from the handle. But you could potentially create something that looks and acts very much like a lightsaber using what's called a plasma torch. Imagine a handle that extends a thin, hollow ceramic rod about 3 feet long. Superheated, glowing plasma would be pumped up through the handle and released through thousands of tiny holes along the length of the rod. This would create what appears to be a blade made of superhot ionized gas, hot enough to melt through solid steel. Once again, the limiting factor is the power source. You'd either need a thick cable connecting your lightsaber to a power plant, or you'd need a major breakthrough in nanotechnology to create a microscopic, incredibly powerful battery. So, handheld ray guns and working lightsabers are definitely Class 1 impossibilities. They're theoretically possible, the physics works, but we desperately need a portable power source with energy density we just don't have yet. Maybe sometime in the next century, with dramatic advances in nanotechnology and energy storage, it could actually become reality. A Death Star, however, is an entirely different story, operating on a completely different scale. To actually destroy an entire planet, you'd need to deliver the energy equivalent of thousands of hydrogen bombs, all concentrated and focused into a single devastating beam. This could theoretically be done using a massive battery of X-ray lasers, with each individual laser powered by a controlled nuclear explosion. A highly advanced civilization, perhaps hundreds of thousands of years more advanced than ours, could certainly engineer and build such a weapon. Or, even more terrifying to contemplate, they could learn to harness and weaponize the natural power of a dying star itself. By carefully controlling and directing the collapse of a massive star, they could actually aim a gamma-ray burster jet at a target planet. A dying star would become the largest, most powerful ray gun imaginable. This kind of planet-destroying technology is so incredibly far beyond our current reach that Dr. Kaku classifies it as a Class II impossibility. It's possible in principle, but it would require a civilization literally thousands of years more advanced than we are. This brings us to one of the most exciting and genuinely mind-bending ideas in all of science fiction: teleportation. Beam me up, Scotty. It's a phrase that has become deeply embedded in our popular culture. The ability to instantly transport a person or object from one location to another would fundamentally change absolutely everything about our civilization. The entire transportation industry would vanish overnight. Armies could teleport soldiers behind enemy lines instantly. You could take a vacation on Mars in the morning and be back home on Earth for dinner with your family. For a very long time, physicists confidently said teleportation was completely impossible because of something called the Heisenberg uncertainty principle. This is an absolutely fundamental law of quantum mechanics that says you cannot simultaneously know both the precise location and the precise velocity of a particle at the same time. The more precisely you know one, the less precisely you can know the other. To teleport someone, you'd theoretically need to know the exact quantum state of every single atom in their body, which the uncertainty principle seemed to absolutely forbid. But it turns out physicists may have been wrong about teleportation being impossible. The key to real teleportation lies in a bizarre, almost magical quantum phenomenon that Albert Einstein himself discovered and absolutely hated. He dismissively called it spooky action at a distance, mocking the very idea. Today, we call it quantum entanglement. Imagine you have two electrons that are created together in a special way so they're vibrating in perfect quantum unison. They are entangled, connected by an invisible quantum thread. Now, you separate them, sending one electron to your friend across town, or even to the other side of the entire universe. According to quantum theory, despite being separated by vast distances, they remain mysteriously connected. Let's say each electron has a property called spin, which can point either up or down. Before you measure it, each electron exists in a strange quantum state of being, both up and down simultaneously. But here's where it gets weird. The very moment you measure your electron here on Earth and discover its spin is up, you instantly, faster than light, know with absolute certainty that its entangled twin, even on the other side of the universe, has a spin that is down. Information has somehow traveled faster than light, which Einstein's relativity says should be impossible. Einstein thought this paradox proved the quantum theory must be fundamentally wrong. But countless experiments over decades have proven that quantum entanglement is absolutely real. You can't use it to send a useful message faster than light. The information you get appears random until you compare notes, but the mysterious connection is definitely real. So how does this strange phenomenon allow for actual teleportation? In 1993, scientists at IBM figured out the answer. They mathematically proved that you could use entanglement to teleport the complete quantum information contained within a particle from one place to another. It works like this, and bear with me because it's a bit complex. Let's say you want to teleport the quantum state of Atom Alice to a distant location where Atom Bob is waiting. You start with a third atom, Charlie, which is specially prepared to be entangled with Bob. Then, you bring Alice and Charlie together and perform a special quantum measurement, a scan, on both of them simultaneously. This scanning process transfers all of Alice's quantum information onto Charlie. But because Charlie is entangled with distant Bob, that information is instantly transferred to Bob through their quantum connection. So Bob now becomes an exact quantum copy of what Alice was. The original Alice is fundamentally altered, destroyed in the scanning process, so you don't end up with two copies running around. Her information, her very quantum identity, has been teleported across space. This isn't just theoretical science fiction anymore. In 1997, physicists successfully teleported a single photon of light for the first time. In 2004, they teleported an entire cesium atom. In 2006, they successfully entangled a beam of light with literally trillions of atoms in a gas simultaneously. Progress is happening at an absolutely incredible pace. Scientists realistically hope to teleport complex molecules, like strands of DNA, and maybe even a simple virus within just a few decades. There is genuinely nothing in the fundamental laws of physics that prevents us from eventually teleporting a human being. But the technical challenges are absolutely staggering, almost unimaginable. It takes some of the most advanced, expensive laboratories in the world, staffed by brilliant scientists, just to successfully entangle and teleport a handful of atoms. To teleport an actual person, you would need to simultaneously scan and perfectly entangle every single one of the approximately 7 octillion 7, followed by 27 zeros atoms in their body, all without losing quantum coherence. It's a feat of engineering so monumentally vast and complex, it might take many centuries, or possibly even millennia. So, teleporting a simple molecule is absolutely a Class 1 impossibility. We might actually see it demonstrated in our own lifetime. But teleporting Captain Kirk across space? That's definitely a Class 2 impossibility. Possible in principle, but realistically a very, very long way off in our future. The technologies we've discussed so far, force fields, invisibility, phasers, and teleportation, are all somewhere on the horizon. They're challenging but achievable. But now we must venture much further out, to the very edge of our current understanding of the universe. We are now entering the far more speculative realm of Class 2 impossibilities. And the first one we'll explore is the dream of every space explorer throughout history, traveling faster than light. In Star Wars, Han Solo pulls back on the hyperdrive controls. The stars suddenly stretch into long, brilliant streaks of light, and the Millennium Falcon disappears into another dimension, crossing the galaxy in hours instead of millennia. But Einstein's special theory of relativity, published way back in 1905, seems to absolutely forbid this kind of travel. He proved mathematically that as any object with mass approaches the speed of light, several strange things happen. Its mass increases toward infinity, time slows down dramatically for it relative to the outside universe, and it physically shrinks in the direction of motion. At exactly the speed of light, its mass would become literally infinite, time would completely stop, and its length would shrink to absolute zero. This is why nothing with any mass can ever quite reach the speed of light, let alone break through it. It's the ultimate cosmic speed limit built into the fabric of reality itself. So, is that the end of the story? Are we forever trapped in our own tiny corner of the Milky Way galaxy, unable to ever reach the stars? Not necessarily. There are potential loopholes. And, ironically, Einstein himself provided the biggest one just 10 years later, in 1915, with his general theory of relativity. General relativity describes gravity not as a traditional force pulling on things, but as the actual curvature of a four-dimensional fabric that physicists call space-time. Imagine placing a heavy bowling ball on a stretched trampoline. It creates a deep dip, a curve in the fabric. A marble rolling nearby will naturally be drawn into that dip and spiral around, as if it's being mysteriously pulled by gravity. Special relativity says you absolutely cannot travel through space faster than light. But general relativity suggests something fascinating. Space itself, the fabric of space-time, can stretch, compress, and warp. And crucially, the fabric of space-time itself can expand faster than light. In fact, in the first tiny fraction of a second after the Big Bang, during what's called cosmic inflation, the universe expanded far, far faster than the speed of light. This opens up two absolutely incredible theoretical possibilities for faster-than-light travel without actually violating relativity. The first possibility is to somehow stretch and compress space itself around you. In 1994, a physicist named Miguel Alcubierre proposed a mathematical solution to Einstein's equations that's now called the Alcubierre warp drive. It works remarkably similar to the famous warp drive in Star Trek. Imagine you're sitting comfortably inside a spaceship that's surrounded by a protective, warp bubble. In front of the bubble, you use exotic matter or energy to compress and contract space-time. Behind the bubble, you expand it. The ship itself doesn't actually move at all through space. It just floats peacefully inside its protective bubble. But the bubble itself, and all the space it contains, is pushed forward by the warping of space-time around it. It's very much like a surfer riding a wave. The surfer isn't moving faster than the wave itself, he's just being carried along by it. Using this principle, you could potentially cross the entire galaxy in a matter of weeks, without ever technically breaking the speed of light locally within your bubble. The second possibility is even more dramatic, to literally rip a hole in space itself. This involves creating a shortcut through space-time, a kind of gateway or tunnel that connects two extremely distant points. We all learned in elementary school that the shortest distance between 2 points is always a straight line. But that's not actually always true in curved space. If you take a flat piece of paper and fold it over on itself, you can bring two distant points right next to each other. Then you could punch a hole through both layers, creating a shortcut that makes the distance between them essentially zero. This is the fascinating idea behind a wormhole, what Einstein and his colleague Nathan Rosen called a MOC, Einstein-Rosen bridge. It's essentially a tunnel connecting two different points in space, or possibly even two completely different universes. Like Alice stepping through the looking glass, you could walk through one end and instantly emerge from the other end, light years away, without ever traveling through the space in between. So why aren't brilliant engineers building warp drives and opening wormholes right now? There's a significant catch, a very big one. Both of these incredible ideas absolutely require a form of matter or energy that is so exotic, so strange, we're not even completely sure it can exist in useful quantities. They require what physicists call negative matter or negative energy. Negative matter wouldn't just be extremely light. It would somehow be lighter than nothing, lighter than empty vacuum. It would be gravitationally repelled by normal matter. If you held a chunk of negative matter in your hand and released it, instead of falling down toward the Earth, it would fall upward, away from the planet. Negative energy is slightly different and perhaps more promising. It actually does exist, but only in absolutely tiny amounts. There's a subtle quantum effect called the Casimir effect, first predicted way back in 1933 and finally measured precisely in laboratory experiments. It shows the two parallel metal plates, placed extremely close together in a vacuum, will mysteriously attract each other very slightly. This happens because the vacuum of space isn't truly empty. It's constantly fizzing with virtual particles, particle-antiparticle pairs that pop into existence and annihilate again in tiny fractions of a second. These quantum fluctuations create a subtle pressure. There are more virtual particles outside the plates than in the narrow gap between them, so they get gently pushed together. The energy density in that narrow gap between the plates becomes less than the energy of empty vacuum. It becomes genuinely negative energy. The enormous problem is scale. You'd need approximately a Jupiter-sized mass worth of negative matter or negative energy to open and stabilize a wormhole large enough for a human to pass through safely. And for the Alcubierre warp drive, depending on exactly how you design it, the energy requirements could be even more astronomically impossible with our current technology. So faster-than-light travel definitely remains a Class II impossibility. It's theoretically possible it doesn't violate Einstein's equations when you include these exotic forms of matter and energy, but it would absolutely require a civilization that has mastered energy manipulation on a truly galactic scale. Perhaps a Type 3 civilization on the Kardashev scale, one that can harness the entire power output of billions of stars. And here's where it gets even more mind-bending. If you can actually travel faster than light through space, or take shortcuts through wormholes, it potentially opens up an even more startling, more philosophically troubling possibility. Time travel. Time travel into the future is actually easy. We're all doing it right now, 1 second at a time, moving steadily forward. If you want to speed up your journey into the future, you just need to travel at speeds approaching the speed of light. This is a well-tested prediction of relativity called time dilation. An astronaut who travels to a nearby star and returns at near light speed will find that many years, perhaps decades, have passed on Earth, while they themselves have aged only a few months or even minutes. They have effectively traveled into Earth's future. But what about the much more problematic idea of traveling backward into the past? This is where physics gets genuinely complicated and strange, because it opens the door to all sorts of logical paradoxes that seem to break causality itself. The most famous is the grandfather paradox. Imagine you build a time machine and travel back to the year 1920. You locate your grandfather as a young man, before he's met your grandmother, and you prevent them from ever meeting, or worse, you accidentally cause his death. You would never be born, but if you were never born, you couldn't have gone back in time to interfere with your grandfather's life in the first place. It's a logical contradiction, a paradox that seems to break the fundamental rules of cause and effect. Physicists have proposed 3 genuinely different possible ways these paradoxes might be resolved by the universe. The first possibility is that you simply cannot change the past, period. If you somehow travel back in time, you discover you're forced by the laws of physics to fulfill a role that history has already written for you. You have no free will in the past. You might think you're changing things, making different choices, but you're actually causing the very historical events that you remember from your own past. It's a self-consistent loop. The second possibility is that you do have free will when you travel to the past, but you are somehow physically prevented from creating any logical paradox. Some unknown law of physics, something we haven't discovered yet, would intervene. If you tried to shoot your own grandfather, the gun would mysteriously jam at the crucial moment, or a bird would fly in front of the bullet, or you'd slip on a banana peel at just the wrong instant. The universe itself would conspire in increasingly unlikely ways to protect causality and prevent paradoxes. But the third possibility, and perhaps the most fascinating from a physics standpoint, is the many worlds interpretation. This theory, which actually comes from quantum mechanics, suggests that every time you make a decision or take an action that could potentially change the past, the entire universe splits into 2 parallel timelines. The river of time literally forks. In one universe, the original timeline, your grandfather lives and you're eventually born. But in the other newly created branch, you've created an alternate timeline, a completely new parallel universe, where your grandfather died young, and you were never born in that timeline. Both universes are equally real, they just can't interact with each other. This many worlds idea seems most consistent with our current best understanding of quantum mechanics. So, practically speaking, how could you actually build a real-time machine? A traversable wormhole is currently the leading theoretical candidate. Remember, a wormhole connects 2 different points in space. But Einstein showed us that space and time are intimately linked together into a single 4-dimensional fabric called space-time. So a wormhole doesn't just connect 2 points in space, it can also potentially connect 2 different points in time. Imagine you somehow create or discover a stable wormhole with 2 openings, let's call them mouth A and mouth B. You keep mouth A stationary here on Earth, and you put mouth B on a spaceship, and send it on a long journey at a speed very close to the speed of light. When the spaceship finally returns to Earth, because of time dilation from special relativity, less time has passed for mouth B than for mouth A. So, if you step through mouth A in the year 2050, you might emerge from mouth B in the year 2030, effectively traveling 20 years into your own past. But once again, you'd need absolutely vast amounts of that exotic negative energy to create the wormhole and keep it stable and open. And there are other serious problems physicists have identified. The radiation and quantum fluctuations building up inside the wormhole throat could become infinitely powerful in a feedback loop, possibly destroying anyone or anything that tries to pass through, or even destroying the wormhole itself. The ultimate answer to whether backward time travel is truly possible probably lies in discovering a theory of everything, a unified theory that successfully combines Einstein's general relativity with quantum mechanics into a single, coherent framework. Such a theory could finally tell us definitively whether negative energy can be created and manipulated in large enough quantities, and whether a wormhole would remain stable enough to actually survive a journey through time. Because it sits right at the very edge of our current knowledge, balanced between what we understand and what we don't, time travel remains a classic Class II impossibility. The idea of splitting timelines and parallel universes brings us directly to our next mind-expanding topic, parallel universes. This isn't just one single idea. It's actually a collection of several related but distinct ideas, all emerging independently from different areas at the frontiers of modern physics. Dr. Kaku outlines three main types of parallel universes. The first type is hyperspace, or higher dimensions beyond the three we experience. We live our entire lives in a world of three spatial dimensions: length, width, and height. But what if there are more spatial dimensions that we simply can't perceive? String theory, which is currently the leading candidate for a unified theory of everything, strongly suggests that the universe might actually have 10 or even 11 dimensions. The extra dimensions beyond our familiar three are just curled up incredibly tightly, rolled up smaller than an atom so we don't notice them in our everyday experience. If we could somehow learn to access and manipulate these hidden higher dimensions, we could potentially perform feats that would seem like pure magic to anyone watching. Imagine a hypothetical, two-dimensional, flatland world, like creatures living on a perfectly flat sheet of paper. A flatlander can only perceive and move in two directions, left-right and forward-back. They have absolutely no concept of up or down, no concept of a third dimension. If you, a three-dimensional being, were to float above their flat world, you would be completely invisible to them, existing in a direction they can't even imagine. You could reach down into their world from the third dimension and move objects around inside their locked rooms. You could disappear from one location and instantly reappear somewhere else by moving through the third dimension. To the Flatlanders, you would seem like a god with impossible powers. The second type of parallel universe is the multiverse idea. This concept also emerges from string theory, or more precisely from its more recent version called M-theory. It suggests that our entire observable universe, everything we can see with our most powerful telescopes, all 100 billion galaxies, is just one single, membrane or brain for short, floating in a much higher dimensional space. This higher dimensional space, this cosmic arena, could be filled with countless other bubble universes, each one a separate membrane floating like soap bubbles in a vast bubble bath. Each bubble universe might have completely different laws of physics, different values for fundamental constants like the strength of gravity or electromagnetism. Some of these parallel universes might be utterly dead, just formless clouds of gas that never formed stars or galaxies. Others might have stars and complex structures, but with physical forces that are too strong or too weak to allow for the emergence of life and consciousness. And in this multiverse model, these bubble universes might occasionally even collide with each other. A few cutting-edge physicists have seriously proposed that our own Big Bang, the explosive birth of our universe 13.8 billion years ago, might have actually been the result of what they poetically call a big splat, a collision between our membrane and another parallel universe's membrane. This idea seems almost like science fiction, but remarkably, it's actually consistent with some of the puzzling data we're receiving from satellites measuring the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. The multiverse idea also offers a possible elegant explanation for one of the biggest, most troubling mysteries in all of science. Why do the fundamental constants of nature, things like the strength of gravity or the mass of an electron, seem so incredibly suspiciously perfectly fine-tuned to allow for life to exist? If the strong nuclear force were just a tiny bit stronger or weaker, stars would either burn out far too quickly or never ignite nuclear fusion at all, making life impossible. If gravity were even slightly stronger than it is, the universe would have collapsed back on itself billions of years ago, long before life could evolve. It's almost as if the universe somehow knew we were coming and carefully adjusted all the settings. The multiverse offers a solution. There are countless universes out there with every possible combination of settings for these fundamental constants. The vast majority are sterile, lifeless. We simply happen to exist in one of the exceedingly rare universes where the settings are just right for stars, planets, and eventually life to emerge. It's a selection effect, not a miracle. The third type of parallel universe comes from the genuinely strange world of quantum mechanics itself. This is the many worlds interpretation we already encountered when discussing time travel. The classic thought experiment that illustrates this is Schrödinger's cat. You place a live cat inside a sealed box, along with a single radioactive atom connected to a vial of poison. If the atom randomly decays, it triggers a mechanism that breaks the vial and kills the cat. According to the standard rules of quantum mechanics, before you open the box and look inside, the radioactive atom exists in a quantum superposition of being both decayed and not decayed simultaneously. This bizarre superposition means the cat is somehow both dead and alive at the same time, which seems completely absurd. The many worlds interpretation resolves this paradox by saying that when you finally open the box and observe what's inside, the entire universe splits into two parallel branches. In one newly created universe, you open the box and find the cat is alive and well. In another parallel universe, physically separated from the first, you open the box and discover the cat is dead. Both outcomes are equally real. They just exist in separate, non-interacting parallel universes. This interpretation suggests that every single quantum event, every random subatomic possibility, causes the universe to branch off into multiple parallel universes. This means there's a parallel universe where you made a different choice this morning about what to eat for breakfast, a universe where the asteroid never hit Earth and dinosaurs still rule the planet, a universe where you're fabulously wealthy, and yes, even a universe where Elvis never died and is still performing concerts. Can we actually travel between these various types of parallel universes? For the quantum many worlds universes, almost certainly not. We have decohered from those parallel branches. Our quantum wave functions no longer vibrate in unison with theirs, so they're forever beyond our reach. For the membrane universes in the multiverse, a journey to another bubble universe might theoretically be possible, but only for an incredibly advanced Type 3 civilization that has somehow learned to harness and manipulate the Planck energy. This is the almost unimaginably high energy scale at which space and time themselves become unstable, and quantum effects dominate gravity, potentially allowing them to literally punch a hole through the fabric of our universe into another bubble. Parallel universes, in all their various fascinating forms, are solidly Class II impossibilities. They're logical, even necessary consequences of our current best and most mathematically sophisticated theories about reality. But actually reaching them or proving they exist would require technology and capabilities far, far beyond anything we can currently imagine. Finally, we arrive at the last category in our journey, the Class III impossibilities. These are ideas that, based on absolutely everything we know about how physics works, should not be possible at all, period. The first and most famous is the perpetual motion machine. This is the ancient, seductive dream of inventors throughout history, a machine that can run forever without any external energy source, or even better, a machine that somehow creates more energy than it consumes. For centuries, countless inventors, some brilliant and some crackpots, have tried desperately to build one. Wheels with cleverly unbalanced weights, magnets carefully arranged to repel each other in a circle. The designs are often ingenious and creative, but they all ultimately fail. Every single one. Why do they always fail? Because they inevitably violate the most fundamental ironclad laws in all of science, the laws of thermodynamics. The first law of thermodynamics states simply that energy cannot be created or destroyed, only converted from one form to another. The total amount of energy in a closed system always remains constant. You absolutely cannot get something for nothing. This law has been tested countless times in every conceivable way, and it holds true without exception, from the tiniest subatomic scales to the largest structures in the universe. The second law of thermodynamics is even more profound and far-reaching. It states that the total amount of disorder, what physicists call entropy, in any closed system always increases over time. You can't even break even. Every single time you try to use energy to do something useful, some of that energy is inevitably lost as waste heat, dissipating into the environment. A 100% perfectly efficient machine is absolutely impossible. This is the deep reason why a car engine gets hot and needs a cooling system, and why your laptop needs a fan to prevent overheating. The second law is also the fundamental reason for aging, for decay, for things inevitably falling apart over time. It's far easier to destroy something than to build it, and that's not just a philosophical observation, it's a law of physics. These laws appear to be absolute and inviolable. But there is one great cosmic mystery that could, at least in theory, possibly offer a potential loophole: dark energy. Astronomers have made an absolutely stunning discovery over the past few decades. The universe is not just expanding outward from the Big Bang, which we've known since the 1920s. It's actually accelerating, expanding faster and faster as time goes on. Something mysterious is actively pushing all the galaxies apart, working against gravity. This completely invisible, anti-gravity force permeating all of space is called dark energy, and it apparently makes up about 73% of the total mass energy content of the entire universe. It is, quite literally, the energy of empty space itself, the energy of the vacuum. But here's the embarrassing problem. When physicists try to calculate how much dark energy there should be using our current best theories of quantum mechanics, we get an answer that is wrong by a factor of 10 to the power of 120. That's not a typo. Our prediction is off by a 1 with 120 zeros after it. It is, without exaggeration, the largest mismatch between theoretical prediction and experimental observation in the entire history of science. We're not even in the right ballpark. We're not even on the right planet. This spectacular failure tells us loud and clear that we are missing something absolutely huge and fundamental in our understanding of the universe and how it works. If we could somehow figure out the true nature of dark energy and learn to tap into this vast reservoir of vacuum energy, could we potentially power something like a perpetual motion machine? Almost certainly not. The amount of dark energy in any local region, like here on Earth, is incredibly, vanishingly small. But until we finally develop a complete theory that can properly explain dark energy, we can't be 100% absolutely certain. Because creating useful energy from nothing would require completely overturning the most fundamental laws of physics that have been tested for centuries, a perpetual motion machine remains firmly a Class 3 impossibility. The final impossibility on our list is precognition, the claimed ability to see future events before they happen. This is a power that has utterly fascinated humanity throughout all of recorded history, from the mysterious oracles of ancient Greece to the prophets described in the Bible, to modern psychics claiming to predict the future. But genuine precognition directly violates one of the deepest, most fundamental principles of all physics: causality. Cause must always come before effect. A glass shatters on the floor after you drop it and it hits the ground, not before. An effect cannot precede its cause. In Newton's deterministic clockwork universe, if you somehow knew the precise position and velocity of every single particle in the universe, you could, at least in principle, use the laws of physics to calculate the entire future with perfect accuracy. The future would be completely determined by the present. But you still couldn't actually see it before it happened. The future existed in principle, but not in reality, until time actually flowed forward. Einstein's relativity theories complicated this picture significantly. General relativity actually allows for exotic solutions called closed time-like curves, which are essentially paths through curved spacetime that loop back on themselves, leading into the past. So time travel to the past is, in a sense, a form of precognition. If you can somehow know what's going to happen tomorrow, you could take action today to change it. But what about somehow passively receiving messages or information from the future without traveling anywhere? When physicists first carefully studied James Clerk Maxwell's famous equations describing electromagnetic waves and light, they discovered something strange. The equations had two distinct mathematical solutions. One was called a retarded wave, which travels forward in time from the past into the future. This is the normal light we see and use every single day. But there was also a second solution, an advanced wave, which mathematically travels backward in time from the future into the past. For nearly 100 years, physicists simply ignored this weird second solution. It didn't seem to make any physical sense, so they just threw it out as unphysical. Then, the brilliant physicist Richard Feynman showed what it really represented. He made a profound discovery. A normal electron traveling backward through time is mathematically completely identical to an anti-electron, a positron, which is the antimatter counterpart of an electron, traveling forward through normal time. So these mysterious waves from the future are actually real, but they represent antimatter particles, not information. They're essential for building a mathematically consistent quantum theory, but they don't allow you to send tomorrow's stock prices or newspaper back to today. They don't actually violate causality in any useful way. There's one more speculative idea worth mentioning: tachyons, hypothetical particles that always travel faster than light through space. If they existed, they would have imaginary mass according to relativity, and the really weird part is that as they lost energy, they would actually speed up, not slow down. It seems like you might be able to use a beam of tachyons to send a message backward in time to the past. But the vast majority of physicists today believe that even if tachyons ever existed at all, it was only in the very first tiny fraction of a second after the Big Bang. They may have been the mysterious particles that caused the universe to inflate exponentially in that first instant, but they would have quickly decayed into the ordinary particles we see filling the universe today. They're no longer a part of our current universe, if they ever truly existed at all. So genuinely seeing the future in any practical or meaningful way appears to be a solid Class 3 impossibility. It would violate causality, and every potential loophole physicists have examined seems to be firmly closed. For true precognition to be real, our entire understanding of physics, built up over centuries of careful experiments, would have to be fundamentally wrong. And so our grand journey through the impossible finally comes to a close. We've seen that some of the wildest, most fantastical dreams of science fiction may actually one day become the practical technologies of our future. We've discovered that the universe is far stranger, far more mysterious, and far more wonderful than we could have ever imagined in our wildest dreams. As we step back and look at the vast landscape that Michio Kaku has painted for us, one powerful, transformative idea stands out above all others. The word impossible is not a final declaration of fact. It's merely a statement about our current level of knowledge and technological capability. Think back just 150 years ago. Some of the most brilliant scientists of the Victorian era confidently declared that, heavier than air, flying machines were utterly impossible, violating the laws of nature. They said that building an atomic bomb was pure moonshine, the fantasy of science fiction writers. They believed that radio communication had no practical future. They thought X-rays were an elaborate hoax when they were first announced. In their time, with their knowledge, they were actually right to be skeptical. The science and technology of their day genuinely did not allow for these things. But science grows and evolves. Knowledge expands relentlessly, and what was completely impossible yesterday becomes obvious common sense tomorrow. What seemed like magic becomes mundane. Dr. Kaku reminds us of a humbling truth. We are still a very, very young civilization. On a cosmic timescale, humanity has just barely climbed down from the trees. We're what's called a Type 0 civilization, still burning dead plants and ancient fossils for our energy. Imagine a Type 1 civilization, which has learned to master and harness all the energy available on its entire planet. Or a Type 2 civilization, which has built structures to capture and use the total energy output of its star, its sun. Or a Type 3 civilization, with the almost godlike power to harness the energy of an entire galaxy containing hundreds of billions of stars. Their everyday, mundane technology would appear to us like pure magic, indistinguishable from the supernatural. This book is not just an entertaining tour of futuristic gadgets and cool ideas. It's a profound lesson in how to think clearly about the future. It teaches us to constantly question our assumptions about what is and isn't truly possible. It encourages a sense of wonder and boundless curiosity, but a curiosity that remains firmly grounded in the rigorous discipline of the scientific method. The most powerful lesson here, especially for someone young and ambitious with their whole life ahead of them, is about the fundamental nature of limits. We are all told, in one way or another throughout our lives, what our limits supposedly are. We're told what is practical for us, what is realistic to aim for, what is possible for someone like us to achieve. But history is consistently written by those brave souls who push past those perceived limits, who refuse to accept impossible as a final answer. So, how can you apply this grand cosmic perspective to your own life, starting today? I have two simple, practical suggestions. First, pick just one idea from our discussion today that truly captured your imagination and sparked your curiosity. It could be invisibility cloaks, quantum teleportation, or parallel universes. Then, commit to spending just 30 minutes searching the internet, but not looking at science fiction movies or fantasy. Look up the real science being done right now. Search for terms like metamaterials research, or quantum entanglement experiments, or M-theory explained. You will be absolutely astonished to discover that the real work being done in laboratories and universities around the world right now is often even stranger, even more exciting and mind-bending than what you see in Hollywood movies. You'll begin to see that seemingly solid line between the impossible and the not yet possible start to blur and fade. Reality is catching up to imagination. Second, and perhaps more importantly, the very next time you hear someone, whether it's a teacher, a boss, a friend, or even that critical voice inside your own head, say that something you dream about is impossible, I want you to pause and ask one simple but profound question. Why exactly is it impossible? Is it truly impossible because it would violate a fundamental law of nature that we've tested repeatedly? Or is it just impossible right now, based on what we happen to know today, with the limited tools and technology we currently have? That one simple question is the key that unlocks an entirely different way of seeing the world around you. It's the crucial difference between seeing an impenetrable wall and seeing a door waiting to be opened. Michio Kaku's remarkable journey began with a childhood love for the fantastic, for the impossible dreams of science fiction. But he realized early on that the true key to unlocking the impossible was not fantasy and wishful thinking, but rigorous physics and mathematics. He devoted his entire life to deeply understanding the fundamental rules that govern the universe, not to be forever limited and constrained by them, but to discover exactly how far they could be stretched, where the loopholes might hide. That is the true beating heart of this book. It's a sincere invitation to dream big, but to dream with discipline and knowledge. To imagine the impossible, but to imagine it with a solid foundation of understanding. The future of the impossible is not already written in the stars, fixed and unchangeable. It will be written by those who study the stars, who understand them, and who dare to reach for them. That was our journey through Physics of the Impossible by Michio Kaku. We've covered tremendous ground today. From force fields to time machines, from invisibility to parallel universes. But I'll be completely honest with you, even the best summary can only take you so far. The real magic, the real transformation, happens when you read the book for yourself, at your own pace. It's in those quiet moments when a particular story or a simple phrase connects with something deep inside you in a way you didn't expect. This summary is designed to help you decide if this book is worth your valuable time. If anything we've talked about today has genuinely sparked your curiosity or made you think differently, I truly encourage you to grab a copy and experience it fully. Reading it isn't just about learning cool facts to impress people. It's a genuine experience that can change the way you see the universe and your place within it. The link to the book is in the description below. Also, if you found this summary valuable and helpful, please take just a moment to hit that like button and subscribe to the channel. It lets us know we're on the right track and helps others discover these ideas. And it ensures you won't miss our next journey into another potentially life-changing book. Let's keep learning and growing together.